All right. Hello, everyone. Welcome back. Today, we are going to be talking about transformations of functions. So, in our last part, in part one, we talked about the rules of the transformations of functions. And we also had talked about some examples of listing the functions. And also, we did not an example, but just an explanation on how we could take a point on a parent function and have that parent function point be transformed as well. All right, so with that said, let's move on to some of these examples. I want to go through today if we have a certain point on a graph, how we could find the transformed point, and also how we could actually graph a sample parent function as well, which is the exponential function. So that's what we're going to be learning today. Okay, so let's start with the example 2. It says the point -4, 10 is on the graph y equals f of x. Find the corresponding coordinates of this point on each of the following graphs. So the first thing that we must do in order to do this, in order to apply this equation here, is we must state what are A, K, D, and C. We have to figure out what those things are. So I'm actually going to copy and paste this because this is important. I'm going to copy and paste this right here. Oh, we already got it. Excellent. I'm also going to copy and paste this. Let's get it blank and put this over here because these are two very, very important things we need to keep in mind when we're doing this. Make this a little bit smaller. Oh, good. Awesome. All right, so let's look at the first example. It looks like A is equal to 1 in this example, right? We just have f of this stuff, so that's the same as 1 times f of all this stuff. So therefore, A is equal to 1. Don't be fooled. Some people say, oh, there's no A, so A is 0. Not the case, right? It's, A times f, right? So if A was 0, we would just have y equals 0. We just have nothing, right? 0 times anything is 0. So A is actually 1 in this case. Then we have 4 here, so K is 4. Then also in our function, we have D is 6, so D is 6. And then C is 0, right? Because we're adding C plus C, so plus 0 would give us the same as opposed to plus 1, right? Because at the end of the day, when we're multiplying, then 1 is our identity, right? 1 is that identity element, whereas when we are adding, 0 is the identity, right? Anything plus 0 is equal to that same number, and anything times 1 gives us that same number. So that's something to keep in mind. And that's a bit of an explanation on how come A is 1 when there's no A, whereas C is 0 when there's no C. So now what I'm going to do is I'm going to use this equation to find the answer to our question. Okay, so we have x over k plus d. So what's x? Well, x is -4 plus k, over k, which is 4 plus d, so plus 6. So that's our x number, or our x coordinate. And then we have ay plus c. So a is 1, y is 10, right? From here, y is 10, plus c, which is plus 0. So this is equal to -1 plus 6, comma 10, which is equal to 5, comma 10, right? So 5, 10 is our new transformed point. And you might notice, oh, hey, the 10 never changed. And that's because nothing outside of the function actually happened. Everything that happened was inside the function. So it only actually impacted x, it didn't impact y. And so it makes sense that that 10 actually did stay the same. Because if we look at what were the transformations applied, it was a horizontal compression by 1/4 that affected this, and then also a translation 6 units to the right. Right, so we only did things with respect to x, not with respect to y, so we did expect the same. Now these next two examples, neither of them will be the same coordinate, so it's not usual that we would get one of the coordinates the same. So let's look at this example, example 2. A is equal to 2, K is also equal to 2, D is equal to 5, and C is equal to 3, right? If we match these numbers up, A with 2, K with 2, D with 5, and C with 3, we can figure that out. So just by doing a quick look at the equation, we can figure out what are A, K, D, and C. Okay, now let's plug it into this equation here. So we have x over k. Well, x is negative 4 over k, which is 2, plus d, which d is 5, we said, comma ay plus c, so 2 times y, which is 10, right? 10 from over here, plus c, plus 3 in this case. And then we just solve. So this is same as negative 2 plus 5, comma 20 plus 3. 323, and there's our answer. And actually, I'm going to highlight the final answers in purple so it's clear what the final answers are. Okay, now for this third one, I encourage you, for C, I do encourage you to try this on your own. However, if you're not feeling ready to, that's okay. But I do encourage you to try this on your own, and then I will take this up as well after we finished. So feel free to pause this video, give this a try on your own, and then we'll see you in a couple minutes. Okay, all right, let's try 2C. All right, so A is negative 3, right? K is a fourth. D is negative 1, right? Because this says plus 1, but there's actually a negative in our equation, so we need another negative in order to make a positive to get positive 1, so that's why negative 1. And then C is equal to negative 3. Okay, very cool. And our original point, let's remind ourselves, is negative 4, 10. So therefore, x is negative 4 and y is 10. So therefore, we have x over k. So negative 4 over 1 over 4. Okay. So 1 divided by 1/4. Okay. Plus, plus d. So plus negative 1, comma, ay plus c. So that's negative 3y plus c. So plus negative 3. Okay. And what's that equal to? Well, this is equal to negative 16 minus 1. And this is equal to negative 30 minus 3. And this is equal to negative 17, negative 33. And that is our final answer. All right, so if you have any questions about that, please let me know. All right, let's move on to example 3. Example 3 says, graph f of x equals 2 to the power of x, and the transformation 2 times f of negative a half x minus 1 plus 3, using at least 4 points. State the domain and range, equations of any asymptotes, and the end behaviors. Okay, so I'm going to assume it's to graph both, which it explicitly states, and also to state the domain and range, equations of any asymptotes, and the end behaviors for both as well. Okay, so let's do that. So for this first one, y equals, or f of x equals 2 to the power of x. This is one of our parent functions. This is our exponential parent function. So what I'm going to do is I'm going to choose some points that I think make sense for this parent function. So the points I'm going to select are going to be, let's see, maybe a half. No, maybe not a half, actually. Let's do 0, 1, 2. Yes, that sounds good. 0, 1, 2, 3. Okay, or we could do a half in there as well, but that wouldn't add much value here. Now, in other parent functions, you might notice we do negative 2, negative 1, 0, 1, 2 as our 5 points. But here I chose 0, 1, 2, 3. And the reason why that is because in this case, we only really have, actually, you know what? let's do some negatives. Let's show what happens in the negative as well. Let's do -2, -1, 0, 1, 2. I think that'd be better actually. It's the square root function that those other numbers make more sense. So sorry about that. Let's backtrack. Let's do this instead. So f of x, this would be 1/4, then 1/2, then 1, then 2, and then 4. So that's our points for our parent function. So let's graph the parent function, like so. So -2, 1/4, 1/2, 1, 2, 4, like that. Okay. All right, and then it says state the domain and range equation of the asymptotes and end behaviors. So I'm going to do that. If you're unfamiliar with things like domain and range, equations of asymptotes and behaviors, we actually will talk more about all of those things in the future, especially this is an exponential function. So there is a whole unit about exponential functions. So do try to follow along, but also don't worry if some of this isn't clear, especially if it has to do with asymptotes and end behaviors. We will talk more about that in the future. Domain and range, though, definitely a good thing to brush up on if that's something you're unfamiliar with or that you've forgotten. Okay, so let's start with our domain and range. So the domain is all real numbers. Now, how do I know it's all real numbers? So my question is there any value for x that isn't valid, right? Is there any possible real number value for x that I can't do 2 to the power of? Well, no, we can do 2 to the power of any fraction, any decimal, any negative number, any positive number, and all of them are always valid. And so the answer is no, there are no restrictions. And if we look on the graph, if we start from our left, and go all the way to our right of the far right of our graph, there's going to be points for everything in our graph as well with respect to x, right? And so, even though it doesn't actually show it the whole domain over the graph, we can see that there's arrows and that eventually the domain will just continue on throughout the entire span. Now, what about the range? So for the range, the question is it true that for every that there is we're able to span all of y as well, right? For if I put in any real number for y or for f of x, is it true that there's some 2 to the power of x value that can get us there? And this is not true, right? Y must be greater than, not greater than or equal to, but strictly greater than 0, right? Now, why is that? Well, let's think about what happens on the domain of 2 to the power of x. If I choose a really, really negative number, right, for x, like 2 to the negative 100, I will get 1 over 2 to the 100, which is very, very close to 0, but is not 0. Okay, let's go further. Let's try to get to 0. 2 to the negative 1,000, let's say. Well, that's 1 over 2 to the power of 1,000. Well, that's even closer to 0. That's much, much closer, in fact, but we're still not at 0. So it can get infinitely close to 0, as close to 0 as we want it to get, but it can't actually get to the real 0. Now, also, is there any way to get a negative number? No, there isn't. No, there isn't, right? Because if we put a negative number for x, then we get a very small number close to 0. And if we put in a positive number for x, then we get, we get a large number, perhaps, especially depending how far into the positives we choose x to be, but it just keeps growing and getting bigger. But there is no way to put any sort of x value in here for x and end up with f of x being a negative number, right? Because it's not -2 to the power of something, it's +2 to the power of something, and +2 to any power, even a negative power, will always get us something strictly positive. Now, we can get close to 0, but we can never actually get to 0, and we can certainly never get past 0 into the negative. And that's why the range is only this. The other thing to notice is if we look at our graph, the graph goes like this. So the graph looks like it expands all the way up. It keeps going all the way up here and it went all the way down to here, but there's a bunch of empty space here. that the arrow will never get to, right? The arrow is pointing kind of to our far left. It's going to go really, really, really far to the left, but not far down. It's not really going down fast enough in order to ever, even if we go really, really, really far down, to ever get to all this empty space. So this empty space, even with the arrows, it will never be covered. And that's the difference between this and our domain for this question, is that the domain, eventually the full domain will be covered with the arrows, but the arrows don't cover the full range. They only cover the top half of everything above 0. They don't cover y is 0 or y is below 0. Very good. Very good. Okay, then we have the equations of any asymptotes. So what is an asymptote? Let's remind ourselves. So an asymptote is a line that the graph approaches but doesn't actually touch. So for example here, the asymptote for the parent function is y equals 2, y equals to 0, that's right. Y equals to 0. Now, why is it y equals to 0? Well, y equals to 0 is this line here. On the entire line, y is 0. And this is the line that this approaches. We get closer and closer and closer to that value, to y equals 0, but we never actually get to this value, right? So at the asymptote, the points are undefined, right? There is no value for y equals 0. Y equals 0 is the invisible line, the asymptote that this graph approaches. Okay, then let's talk about end behaviors. So what we want to do for end behaviors is, as x approaches infinity, f of x approaches what? And as x approaches negative infinity, f of x approaches what? So let's see, as x approaches infinity, so as x gets closer and closer and closer to this side, what happens with y? Well, it looks like y is going up too. As x goes up, y goes up. In fact, y goes up much faster than x. So as x approaches infinity, f of x approaches infinity as well. Now, what about this one here? If as x approaches negative infinity, so as we're getting closer and closer along this line, what does f of x or y approach? Well, we already answered that with our asymptote. We said it approaches 0. It's getting closer and closer and closer to 0, right? The further negative we put the x value, the closer to 0 it is, and the further up, the higher we make our x value, when we make that x value higher, 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 the y value also gets higher and higher and higher, and in fact at an even faster rate than x does, right? We move x up 1, and f of x doubles from the previous value, which is very powerful, than just adding 1, right? So that's the answer for our parent function. So all that work, I know, and we still have the transformed version of the function to do as well. So let's do that. So what are the transformations here? Well, instead of listing the transformations, it doesn't actually ask us to do that. I'm going to just write down what are a, k, b, and c. So a is equal to 2, k is equal to negative a half, and d is equal to 1, and c is equal to 3. So I'm going to put all of those into this equation to get my new points. Oh, there we go. I'm going to get my new points, and I'm going to put them in for the new graph. Okay, I wish I had more room here. I'm just realizing, actually, you know what? I'm going to erase some of this stuff so we have more room. We already did this question. So, okay. So for f of x is equal to, or we'll just say transform function. That's a lot to write out. Transformed function. Okay. So we want to start with all of these points. Let's start with the very first point. Okay. All right. -2 over negative a half plus d, so plus 1, comma, ay plus c. Okay, so 2 times y, which in this case y is a fourth because we're doing this first point here. Actually, I'll highlight it as we're doing it. We're doing this one right now. Plus c, so plus 3. Okay, so this is equal to 4 plus 1, comma, 3.5, which is 5, comma, 3.5. So that's our answer. 5, comma, 3.5. Okay, let's do the next one. So I'm going to actually remove my highlight here and I'm going to highlight the next one. Let's do this one next. And it said using at least 4 points, so I actually might just go through the first 4 and then stop there. They only actually needed 4 points from us. So negative 1.5. Okay, so negative 1 over k, which k is negative a half, okay, plus d plus 1 times a times y, so 2 times a half plus c plus 3. So this is equal to 4 over here, right? And this is equal to 2 plus 1, which is 3. Okay, so 3 and 4, wonderful. Let's do the next one. I know this is repetitive, it's the same stuff over and over. So do feel free to pause, try these yourself, and come back as well if you'd like, but I will continue here as well. Here we have 0 over negative a half, which will just be 0 plus d, so plus 1, comma, ay, so 2 times y, 2 times 1 plus 3, so that's 1, comma, 5. Very good, 1 and 5. And let's do one last one. Let's not bother with the 2, 4 because they only actually asked for 4 points at least. We could. There's nothing wrong with that. It only says we have to do 4 points, so I'll just do 4. So here it's 1 over negative a half plus d, so plus 1, comma, ay, so 2 times y, 2 times 2 plus c, so plus 3. So that's equal to 1 over 1 over 2. Okay, so that's negative 2 plus 1, comma, 4 plus 3. So that is negative 1, comma, 7. All right. So let's plot these points as we normally would. And that should be here. Negative 1, 7. Okay, so it looks like they're going to go somewhat like this. Something like that. And if we think about what's being done here, it's, should have been vertical stretch by 2, horizontal stretch by 2, also reflected in the y-axis, which looks like it was, and then also moved over a bit as well. That looks about right. Now it also asks us to state the domain and range, the equation of the asymptotes, and the end behaviors. So what I'm going to do first is let's do domain and range first. So domain, first of all, is the same. It's just going to be all real numbers. Range, on the other hand, has changed. Range must be y is greater than 3, right? Now why? Why is that? Why must the range be greater than 3? Well, in this case, we added 3, right? We went up by 3. So rather than approaching 0, we're going to be approaching 3 this time. All right. Then we have our equations of our asymptotes, which are, we have y equals to 3, right, rather than y equals to 0, because just as this went up, right, so did, just as we moved up, so does our asymptote, right? When our whole graph moves up, so does the asymptote. It also moves up. Okay, we also, what else do we have as well? Well, we also have the end behavior. So that's going to look like this. As x approaches infinity, f of x approaches something. And as x approaches negative infinity, f of x approaches something. All right, so as x approaches infinity, looks like, well, it's happening on this side now, right over here. So it looks like y is approaching, the asymptote is approaching 3. And as x is approaching negative infinity, as we're getting further and further to our far left over here, right, with respect to x, y is also y is actually not also, I should say y is increasing, right? While x is decreasing, y is increasing. It's going up all the way up to infinity. So the answer is infinity here. So it's kind of like they swapped, right? But before, the end behavior was that as x approaches infinity, f of x approaches infinity as well. And then for the other one, it was it approached the asymptote. Whereas here, our first one, it approached the asymptote. And that has to do with this negative sign here, right? Because we swapped, we went and we did a reflection across the y-axis, and so that's why that happened. All right, so there are some suggested textbook problems for you guys to try, so best of luck with those, and let me know if you have any questions. But that is everything for the transformation of functions today. Next time we will talk about adding and subtracting polynomials, so we will see you for that. Bye for now.